Sometimes a new idea in science is so strange, so completely out there, that it terrifies the very people who should be the most excited about it. Well, today we're talking about one of those, a theory that was born from one man's obsessive quest for mathematical beauty, and in the process, accidentally uncovered a whole new reality. This is the story of Paul Dirac and the bizarre discovery of antimatter. Let's get into it. So, here's how we're going to break it down. First, we'll see the absolute crisis his theory caused. Then, we'll look at the impossible problem he was trying to solve in the first place. We'll follow his strange but brilliant mind as he built this new equation, and then we'll see the monster it unleashed. And stick around, because we'll get to its stunning vindication and the truly cosmic mystery it left us with. All right, picture this. It's 1928. A quiet, almost painfully shy young man named Paul Dirac gets up on stage to present his latest work. He speaks in this flat monotone, very detached. But what he's about to say is going to set off an intellectual earthquake. After he's done, Werner Heisenberg, this is a titan of quantum mechanics, is so profoundly disturbed that he calls Dirac's theory the saddest chapter in modern physics. Now, this wasn't just, some academic disagreement. This was a cry of pure despair. And it gets even better. His colleague, the famously sharp-tongued Wolfgang Pauli, supposedly has an even more wild reaction. The story goes that he just threw his hands up and declared he was quitting physics altogether to go write a novel. Think about that. The theory was apparently so absurd, so nonsensical, it was literally breaking the minds of geniuses. So that's our mystery right there. What on earth did Paul Dirac cook up that could provoke such a deep crisis among the very pioneers of the quantum revolution? What did he show them? Well, the problem Dirac was wrestling with was the single biggest headache in physics at the time. He was trying to bring together the two great pillars of modern science that, honestly, just did not want to play nice with each other. So on one side, you've got Einstein's relativity. That's the world of the very big and the very fast. It's all about smooth, continuous spacetime. But on the other side, you have this new weird thing called quantum mechanics. This is the world of the very small, and it's all about probabilities, weird jumps in energy, and just general uncertainty. They were like two completely different languages trying to describe the same universe, and they just could not be reconciled. And this brings us to our guy, Paul Dirac. He was famously known as the strangest man. Seriously, this was a man of so few words that his colleagues joked they invented a new unit of measurement, the Dirac, which meant speaking one word per hour. But under that silent surface was a mind obsessed with a single idea: mathematical beauty. He truly believed that a fundamental law of nature had to be beautiful, so he set out to find it. Now, someone had already tried to build a relativistic quantum equation. It was called the Klein-Gordon equation, but it had a fatal flaw. Because of the way the math was structured, the equation could sometimes spit out answers that were just complete nonsense. Like, it could calculate the chance of something happening as a negative number. What does that even mean? You can't have a negative 20% chance of finding your keys. It's impossible. Dirac's opinion on this was, well, classic Dirac. He called it physically nonsense. And for him, that was it. This ugly little mathematical problem wasn't something you could just ignore. It meant the whole thing was wrong. He had to start over from scratch. So, Dirac goes on this personal quest. He needs an equation that is mathematically simple, what physicists call first order in both time and space. He wanted something symmetrical, elegant, and above all else, beautiful. And the way he got there was just a masterclass in creative thinking. He knew he needed a simple, linear equation to get around the problems of the old one, but he hit a wall. Just using regular numbers wasn't working. Then, he has this flash of genius. He decides to use matrices, these grids of numbers that have a really weird property where the order you multiply them in actually changes the answer. After trying some smaller ones, he takes this huge intuitive leap and realizes that only bigger, 4x4 matrices had the right kind of structure to make his beautiful equation work. And what he came up with was, well, it was exactly what he was looking for. It was elegant, it was symmetrical, it was just profoundly beautiful. He had finally forged his perfect equation. The only problem? This beautiful creation was hiding a truly monstrous secret. And here is the big twist. On one hand, the equation was a massive success. It worked perfectly for electrons moving near the speed of light, and get this, just from the pure math, it naturally predicted a property called electron spin, something that scientists had seen but just kind of tacked on to other theories before. But remember those 4x4 matrices? They meant the equation had 4 solutions. Two of them describe the electron's spin, think of it as spin up and spin down, but the other two, oh boy, the other two described electrons with negative energy. And that's not just weird, it's an absolute catastrophe. It would mean that every atom in the universe could just spiral down into an infinite abyss of negative energy, collapsing instantly. This was the monster that horrified Heisenberg and Paul. So for 3 years, Dirac was basically ridiculed. His beautiful equation looked like a beautiful failure. But here's what makes him a legend. Instead of giving up on it, he did something incredibly brave. He decided to take the monster seriously. In 1931, he stood up and said, "What if these negative energy solutions aren't a mistake? What if they're describing a brand new kind of particle? An anti-electron, a perfect mirror image of an electron, same mass, but with an opposite positive charge." He predicted a particle that no one had ever seen, based on nothing more than his faith that his beautiful equation had to be right. And what happened next is just wild. The proof came so fast it's almost hard to believe. Just 1 year after he made this crazy prediction, a physicist named Carl Anderson is looking up photos of cosmic rays, and there it is, a little track curving the wrong way, a particle with the exact mass of an electron but a positive charge. He called it the positron. And boom, the very next year, Dirac is in Stockholm, accepting the Nobel Prize. His beautiful monster was real. So, Dirac's theory was proven right in the most spectacular way possible. But discovering one little antiparticle was like opening a door to a much, much bigger mystery, one that gets to the very core of why we're here at all. See, the beautiful logic of his equation didn't just work for electrons. It implied that every single particle of matter should have an antimatter twin. There should be antiprotons, antineutrons, the whole shebang. An entire shadow universe of antimatter had to exist. And this leads us to a giant paradox. Our understanding of physics says the Big Bang should have created matter and antimatter in perfectly equal amounts. But here's the thing. Whenever matter and antimatter touch, they annihilate each other in a flash of pure energy. So, logically, everything should have just canceled everything else out, leaving behind a cold, empty universe filled with nothing but light. But, look around. We're here. This means that for some reason we still don't understand, that initial cancellation wasn't quite perfect. Our best guess is that for every billion particles of antimatter created in the Big Bang, there were a billion times 1 particles of matter. And that tiny little leftover scrap, basically a cosmic rounding error of 1 part in a billion, is everything. It's every star, every galaxy, every planet, and every single one of us. Which leaves us with the ultimate question, the final mystery born from Dirac's beautiful and monstrous equation. In that primordial cosmic battle between matter and its opposite, why was there a survivor at all? Why did matter win? And that, right there, is still one of the greatest unsolved mysteries in all of science.